let's look at an example of static equilibrium. In this picture, these kids, they are sitting still on the seesaw that's free to do this, but they're not rotating. They're in balance, they're balanced with each other, and so it's not going up and down, and it's not going up and down this way. So it's not rotating, nor is it in translation in any way whatsoever. So what does static equilibrium look like in this? Well, there are several forces going on, right? There is the force upward on, and we're looking at the static equilibrium of the plank that they're sitting on. There's the force upward on it. So that force is up. And then there are two forces downward on it. There's M1G, and this is, I'm going to put in the, that is minus J hat direction. And then over here, there's M2G, and that also is in the minus J hat direction. And what does that tell us? That tells us that F plus this, which is minus M2G J hat, plus this, which is minus M1G J hat, has to equal 0 for us to be in equilibrium. Okay, that gives us what F is right away, because we now know that F is M1, I'm just going to do a little algebra here to simplify, G J hat. F is in the positive J hat direction, and it is exactly equal to the magnitude of the downward weight of the two kids. So that's what it means to have translational equilibrium. But now let's look at what happens with the torques, as we've written here, right? The torque due to one kid is M1G R1. The torque due to the second kid is M2G R2, but it's opposite to the first one. What does positive versus negative look like? And I've written this backwards from the picture, so I'm going to edit that real quick. We'll call this 1. We'll call this 2. Okay, so we now have 1 and we have 2. We have a distance R1 and we have a distance R2. So what we're after, this was sum of the forces equals 0. So whatever the forces are, which is the force of the pivot point minus the weights. All right, now we're after the sum of the torques equals 0. What are the torques? Which ones are positive? Which ones are negative? How do you figure that out? Well, if we look at 1, right, this kid is going to cause a counterclockwise rotation, right? And so by the right-hand rule, counterclockwise rotation, that's going to be out of the board towards you. That's a positive torque. So when we look at the sum of the torques, right, the first one is positive M1G times R1, and that's going to be out of the board towards you. I'm going to call that the K hat direction. Okay, so that's the first one. Out of the board towards you, that's in the K hat direction, that's positive. What's the second one? The second one, M2G. What's that going to cause this system to do? Well, that would cause a rotation in this direction. That is a counterclockwise rotation back towards me. And since it's a counterclockwise rotation back towards me, that's negative. And that all has to be equal to 0. So M1G R1, and you can see the direction, since everything's in the same direction, the direction at the end of the day doesn't matter. You just have to get the signs right. So we've got two equations. We've got FP is M1 plus M2G, and we have the total torque, which is going to be m1 r1 minus m2 r2 onto g equals 0. And now we know everything about this system. Once we know the masses, we can figure out the forces. We're all set, right? We need to know the force, the distance. And this is in a simple system that you've probably played with as a kid.